we're going to talk about how instruments make music. So first we're going to talk about stringed instruments. So stringed instruments have a string that is attached at two ends, and the one end is fixed. It's probably the bridge or where the string attaches to the instrument. The other end is going to be where it's also attached to the fingerboard or where you put your fingers down. Where you put your fingers down changes the length of the string. So each end acts as a node. So it's a fixed end. So when we talk about reflection, basically the longest wavelength that I can get where I have both ends being a node that doesn't move is going to be half of a wavelength. So that half of a wavelength is my fundamental frequency. And that wavelength is half, so the length of the string gives me half a wavelength, or one full wavelength would be twice the length of the string. I can also get the next largest wave that I can get, smallest wave I can get, has the nodes here and has one extra node here. So it's one full wavelength. It's not very well drawn, but it's one full wavelength. So it's twice my fundamental frequency. And then I can get three of these things in there. So my next fundamental frequency that I can get is, or my harmonic is 3 times the fundamental frequency. So I can have a question that asks, if the frequency produced by a guitar string is 587 hertz, the speed of the wave is going to be 600 meters per second. What is the length of the string? So the string vibrates at a rate of 600 meters per second. And so I use velocity is equal to F times lambda. Frequency is 587. I rearrange to solve for lambda. So it's 600 divided by 587, which gives me 1.02 meters. That's my wavelength. The length of my string that I will have is going to be half that, or 0.51 meters. So if I want to have the lowest note that I can have on an instrument that it will produce is going to be determined by the length of the string, which makes sense. So the bass, double bass instruments, which have the lowest notes, are going to have the largest bodies, the longest strings. And if I want to get higher notes, I put my finger down to shorten the length of the string. And if I were looking at this, if that's my frequency, then the 2F would be twice this, the 3F would be 3 times this, and those would be the harmonics that I would hear. So closed end pipes is where you have your mouth covering one end and then the other end open. So the mouth covering the one end would be like a trumpet or clarinet, you're breathing into it. And it's open at the other end, it's the bell or the end of a recorder. So the mouth, the closed end, acts as a node. The open end acts as an antinode, which means that when I draw my waves and figure out what waves can fit in there, this end always has to be the part that doesn't move. This has to either be a crest or a trough. So the longest or the most fundamental frequency that I can put in there is 1/4 of a wavelength. It's like half a crest or half a trough. That's my fundamental frequency. And so the length of my pipe is actually 1/4 of the longest wavelength that I can produce. The next thing that I can get there where this is still a crest and trough and this is still a node is I can fit in 3/4 of a wavelength, right? This is half and this is a quarter. So the next harmonic that I have is not actually 2F1. It's not the second harmonic. It's actually the third harmonic. So 3F1. And then so on and so forth. All the harmonics in a closed end pipe are going to be in 1/4 interval wavelengths. And they're all going to be odd number multiples, right? So they're going to have 1/4 wavelengths. And so they're going to be odd number multiples of my fundamental frequency. So I can't have like one full wavelength. I can't have 1.5 wavelengths. They have to end in 1/4 of a wavelength. And so what happens is that it changes the complex wave that comes out of it. So the complex wave, remember, is a combination of the frequencies that I get out of it. If I can't get the second or the third, the fourth or the sixth harmonic out of this, it's going to change what my complex wave sounds like, which is why a trumpet or a clarinet sounds different from a violin or a double bass. An open-end column, and not as many instruments are open-ended columns, also sounds different. So a flute, even though it comes from the same family as a clarinet and a saxophone and things like that, or even a recorder, sounds differently because it is an open end column. So it's an open end column because at the front end of it, you're blowing across it. So air can also come out of the pipe. And then air also comes out of the end of the instrument that's opposite the mouth. So you have two open ends. The ends always act like antinodes. So this always has to be where the crest or the trough are, and the node ends up having to be somewhere in the middle. So this is the same thing as this, so I can treat it just like a string. So it turns out the lowest note that a flute can play has to be twice the length of, sorry, the length of the instrument has to be twice the length of its longest wavelength that it can produce. Whereas here, the length of your instrument is going to actually be able to produce, I can produce a much longer wavelength with the same length of tubing, right? Here I can only get half a wavelength. Here I get a quarter of a wavelength. So what that means is that the same length of instrument between a flute and a clarinet, which pretty much are the same length, have a different range. Because the clarinet is closed end, I can have the same length of tubing resulting in a wavelength that is twice as long or is twice as low as a flute, which is why the clarinet range is more in an alto range and the flute is more in a soprano range.